but everyone is here and thank you have the stage. Thank you.
Okay, I want to thank the organizers for this incredible conference. And so our goal today is to gain some understanding of an isomorphism group homology. This is one of the main theorems of Martinello, Davis, and Schwann and myself. So the homotopy theory makes us study a certain group homology, that is, the bodons equalize the group which acts upon the table. And after inverting P from this, there's an isomorphism with a different group homology. I'm going to write it this way, where it's continuous homology of the group GL and C. Coefficients in yes, we know what this is. It's scalar algebra and generators of various degrees that we know, but I want to provocatively write it this way as the homology of a certain group, because I think this fits the pattern of which this is the T equals to 0. Okay, great. This is going to be an application of Falking's theorem, which I've been calling the two towers isomorphism. It goes like this. So, on the one hand, we've got unit states, LTN0, form the diamond associated to this and quotient by the Moran stabilizer group P. So LTN is just the adic spectrum of AN, and the 0 means invert P on that, take the generic fiber. The diamond symbol means just restrict the Yoneda functor of this to perfectness. On the one hand, you've got this stack. On the other side, there's Drinfeld space, Drinfeld symmetric space of dimension n-1. And we mod out by GLNZ. And the form of Falking's theorem already suggests there really ought to be a strong connection there. Like, there should be some homology theory with coefficients in the structure sheaf, which just outputs this here and this here. Kind of see why the geometry liquidates here. Still, though, we have a ways to go. But before even doing that, I wanted to motivate where did this theorem come from in the first place. So let's do that. So this I think will be on context. Where this theorem. Where did it come from? Okay. So a good place to start might be to involve a very different setting, a very classical setting, Riemann's classification of abelian varieties over the complex numbers in terms of linear algebra. So we have on the one hand the groupoid of abelian varieties A over the complex numbers. And this is going to be an equivalence with a different groupoid, and that's going to be, well, the way I can say it briefly orally is like it's polarizable odd structures of weight negative 1. But let's write down what that means in terms of the actual objects involved. Right, this way in terms of pairs T complex. And the T here is supposed to be a I should have said abelian varieties of dimension G in the one hand, yeah? And the T here is going to be an abelian group that's going to be isomorphic to Z to the G. In other words, it's a free abelian group of range. I'm not specifying a basis to it. And the W is going to be a subspace of T tensor C. And the W here had better be dimension G. So W is a complex subspace of the vector space T tensor C. And together, the pair T comma W has to satisfy some condition. There has to be a polarization, but I'm not going to write that very detail. So I'm just going to write polarized. I mean, that's the condition that guarantees that the complex torus W modulo T is going to be in a variety rather than just a complex torus. There needs to be a projective embedding or a line bundle. Okay, given an abelian variety, what is the T and what's the W? So T here is going to be the homology of A with C coefficients, right? So that's going to be rank 2G, no one corrected me of those 2G here, fine. And then the W is going to be the Lie output thing. It's a complex vector space. And basically, the embedding of W with the T tensor C is like the Hodge decomposition. Phrased in terms of the first homology. If you prefer, you can take the dual of all of this stuff to get a Hodge structure of weight 1 rather than with -1, but then it would be an anti. What? All right, any questions on that? So what we want to do is turn this into a sort of theoretic statement about formal groups. Because formal groups, in some sense, mimic the behavior of a dual interrupt. So the sense that there's a version of this for formal groups, but more generally, T physical groups. And to set this up, I need first an analog of complex numbers. And easy to do that. So let C be a complete algebraically closed field containing QP. So the metric is going to extend the p-adic metric. So if you like, C is the completion of the algebraic closure of QP is a perfectly good example. And the thing that we want to classify is not abelian varieties, but rather formal. And actually, not just any formal groups. Formal groups in question are going to live over OC. OC and not C. In C, P is invertible, and our theory of formal group is really boring, isn't it? Everything is isomorphic to the end. And it's only interesting in all of this. And not just that, I actually want to exclude the additive group from consideration here. I want to make an assumption that when you base change gamma to OC mod P, the thing has positive height. I want the height to be n. Let's just fix an n, and now we're talking about this thing. And this is exactly the sort of thing that comes out of studying these moduli problems that we were considering before. In fact, all this is on the left side of this, is going to be the C points of a certain stack. What stack is it? It's that stack. C points of that stack. Why? You have to remember what LTN0 was doing. It was classifying deformations of a height and formal group to OC. But I've modded out by GN. And so that has the effect of killing off the identification of the mod P gamma with the fixed gamma n. So you've lost that information, you've lost that structure. So this thing on the left is exactly this. All right, great. So this category over here fits into a larger category. And I haven't set the word P divisible groups yet, and it's a whole thing if you've never heard about them before. I'm going to try to be quick. P divisible groups, and I'll use the letter notes. H and G. Just H. Over those. So, given such a formal group, given such a formal group, what you can do is consider the p-powered origin in that group. That is all of the, the power series defining multiplication by p to the n You can Weierstrass prepare it. You could write it as a polynomial times something through. So the condition of vanishing that p to the n power torsion actually defines a finite group scheme over OC. The rank of that group scheme is p to the n times n. And if you consider all of those group schemes at once, you get what's known as a p-divisible group, or Barsadi-Tate group. It's something completely algebraic in nature. It's a co-limit of all of these finite group schemes over whatever base. And this gadget is actually very, very useful. In some sense, it contains, it's somewhat more flexible than formal groups. Well, they each have their advantages, but the notion of height on the formal group is actually fixed as you base change from one context to another, whereas that's not true for formal. So we're in a little bit of a tighter analogy between a p-divisible group and okay. As an example of a p-divisible group, is a really dumb example. It's constant. In p modulo z, certainly that's an abstract p-divisible group. If I put an underline under it, that's going to be a constant p-divisible group. The height of this is going to be 1. And this is an example of a constant or an étale p-divisible group. It's certainly not formal. Whereas an example of a formal p-divisible group would be the group of all p power roots of 1. That's just the torsion in the multiplicative p-divisible, in the multiplicative formal. And that one actually is formal, whereas it's not. So there's some kind of dichotomy between étale and connected. They're kind of poles, they're opposites. But generically, a p-divisible group will have an étale part and a connected part. These are the two extremes, one and the other. About this.
The left-hand side is the points of some interesting quotients. The right-hand side, the points of anything interesting.
Oh, the left-hand side is, oh, well, we're getting there right now. Yeah. Yes. Oh, I should say something like the image of here and here is the connected. So the image is the connected p-divisible groups. And by connected, I mean all of these group schemes, their underlying scheme is connected. All of the points are stuck to the origin. You can see this is going to be true of mu p infinity over a base like OC.
You have to make some assumption on the formal group being divisible.
That's my assumption. Because look, if you reduce mod p, and I'm telling you that that's height n, positive height means p divisible. And you can export that result from mod. Okay. All right, the theorem in our paper about p-divisible groups is a classification of p-divisible groups over OC. That's along the line. It goes like so. P-divisible groups, H over OC, all of them. So that, that category. Let's restrict them to be height n. Is in correspondence, once again, it pairs T homophily. And the T here in question is going to be isomorphic to Z to the power of n, although the isomorphism is not included with the data. Just T is a free ZP module of rank. And the W is going to be a sub vector space of T tensor C, and then I need to put a little tape twist here, which you should definitely ignore right now. But it really resembles what's going on over there. There's no condition of there's no condition of polarizability involved here. That's somehow a global condition that only involves algebraic variety. What's the T and what's the P? Okay. I mean, it's rather similar. If I have a p-divisible group H, there's always a tape object. And that's going to be, and I mean, in some sense, it's the homology group of H. the ZP coefficients, maybe ad hoc definition of this, like, limit of all of the points of the constituent, the limit over n, all of the constituent layers of diffuse. So this is the Tate module of H, and this is going to be free of rank n, essentially by definition of height. Yes,
Does this make sense because it's also C points?
it's also C points. That's true.
That's how I see it.
These are finite group
Yeah.
schemes, and OC is integrally closed in C, and so yes, it's also the C. And then the W is the Lie algebra of the groups, which actually makes sense. It's the well, you have to do some work to define what is the Lie algebra of a P divisible group. But suffice it to say, the Lie algebra maybe behaves as you would expect. It's something to do only with the behavior around the origin. So for instance, the Lie algebra of UP on Z, the étale P divisible group, who knows what it is?
0.
0. It could be 0 because QP mod ZP is discrete. There's nothing going on around the origin, or the origin is isolated. Whereas in the algebra of UP infinity, well, oh, sorry, I guess this should be the Lie algebra tensor that was as it is. Yeah. You get an OC mod. Whereas the Lie algebra of UP infinity, that's connected. It's going to have a non-zero Lie algebra. It's going to be just free of rank 1 over OC. In fact, the Lie algebra of a formal group agrees with the Lie algebra of its corresponding. So if you want to pick out the étale objects over here on the right, those are just the ones where the W is equal to 0. So the dimension of W is determining the dimension of the H. All right, great. So now we can talk about where Falkington's isomorphism came from, at least when it comes to classifying the OC points on either side. The full theorem takes more work than that. So on the, okay. So let's answer this question. Which pairs T on the W correspond to one-dimensional formal groups over those, since after all, that's what we want to classify. We don't want to classify all P divisible groups, we just want to classify these ones, the ones that actually come from formal groups of dimension 1. So, of course, the W has to be one-dimensional. Great, but we also need to guarantee that the group is formal. So that means that the P divisible group is connected, and that means there's no étale part. So we need to we also need the non-existence of any morphism, non-zero, from H to the constant P divisible group. Think about what that would mean. In terms of the pairs T comma W, we have T, W over here, and this would map to, okay, what's the Tate module of QP mod ZP? It's just ZP. And that would just be 0. So this map from T to ZP would be like a linear form on T, which is non-zero. And that non-zero form would have to vanish on W. Now really think about what this means. It means that W is not contained in any QP linear subspace in T tensor C. So in other words, T tensor C, of course, it has this QP structure to it because it came from something defined over ZP, in fact. So if it were contained in such a subspace, there'd be a QP linear form that vanished on the W. And then you would get a non-zero map like this. And then the thing wouldn't be connected. All right, great. So the conclusion is that the stack, which classifies such things, so that's going to be LTN0 modulo GN. This should correspond with situations where, okay, we've got a T and we've got a W. You know, if you trivialize the T, then the W lives in the projective space Pn minus 1. So if you think of it this way, I put this in a little box to explain this. The line W, it really lives in Pn minus 1 of C, doesn't it? After you've trivialized T. So if T is really Zp to the n, then W is a line in T tensor C. So W determines a line there. But the condition that W is not contained in any P linear, QP linear subspace means that actually this W lives in Drinfeld space, meaning the complement inside of this projective space of all QP linear hyperplanes. Great, but we've trivialized the T. To untrivialize the T, you should mod out by the automorphism group of that trivialized T, and that's GLNCP. So at least this is true on C points. There we go. So there's my little motivation for why these two stacks should be the same. At the very least, they agree on C points. I think that's a pretty satisfying explanation. However, it is not a proof. We've only established it for C points. I'll have to go for you to our paper for them. General. All right, any questions on this? Go ahead.
Can you repeat again why it exists in the upper half plane?
Right, so what is the p-adic upper half plane? It's the complement in projective space of all QP linear subspace. What's a QP, all QP linear hyperplanes? What is a QP linear hyperplane? It's the vanishing locus of a QP rational linear form in n variables. If W was contained in such a thing, then there'd be some linear form that vanished on W. But that linear form would define a map from here to here. And then you would get a map from H to QP mod ZP that's non-zero, and then H would be disconnected. So the key factor is that H is connected, and that's exactly what forces you to live here. Okay, great.
Sorry, maybe this is a naive question because I'm not familiar with it, but I remember there's a terminology called Giordani theory, which classifies this sort of thing. I mean, in very general, I mean, I remember the base could be quasi-regular, quasi-atomic. I remember, for example,
Confession, I don't know what quasi-symptomic means, not even a little bit. So I'm afraid I can't answer right now. But you did say Giordani module, so just hold that thought. At the end of this talk, they will read it. Okay. Great. All right, so oh, great. So any others? We're gonna like kind of change direction right now. All right, great. So we want to apply the theorem, right? We want to get some comparison, which gives us access to cohomology. So the cohomology is going to be geometric in nature. We want to take some kind of cohomology groups on either side and somehow test it. Those cohomology groups are pretty complicated, and I want to do one basic example first, and those examples come from just one point, QP, or spec QP, or spot QP, whatever. And so this section is called accent theory. And it's going to be quick. Okay. So I'm going to start with a, well, yeah, I'll pose a challenge to you. So CP, this field CP, it's going to be QP bar and then hat. Great. And then that field admits an action by the Galois group of QP bar over QP. I mean, the Galois group acts continuously on QP bar because it preserves the p-adic topology. So that action extends to the completion. And my question for you is, what is the fixed points? So if you were to take the CP and then consider all points fixed by the entire Galois group, what would you expect to get? QP. But I want you to realize that this is not obvious. Because why couldn't there be an element of CP, it's transcendental, and it just happens to be fixed by every element of the Galois group? I just want you to pause now and think that that's not super obvious, that there shouldn't be such a thing. But it is true, and this is a theorem of Ax from, I can't remember exactly the year, but sometime in the 1960s. So this theorem is not so hard to prove if you're just interested in fixed points. But this is, these are homotopy theorists here, so you're probably interested in homotopy fixed points. So what is the cohomology, the complete cohomology of this acting on this? That's a good question. And the answer is like actually pretty interesting. So this is a theorem of Tate from 66, I think, in his paper on p-divisible groups. So he computes the cohomology of this on this, that is the continuous cohomology. Here, just write it this way. Continuous cohomology of the Galois group of QP R over QP acting on CP is isomorphic to, okay, the H0 term is just going to be QP, that's Axis theorem. But there's one more term which lives in degree 1. I'm going to write it this way. Epsilon is degree 1, and of course it squares to 0. So there's one class in degree 1. This theorem's incredible. The Galois group of QP is extremely complicated. There's no notion of generators and relations for it. It's like just huge and complicated. However, its cohomology behaves as if it were the cohomology of some abelian group, in fact, a cyclic group. So where does this theorem come from? Yeah, I'll go. Well, I want to go over Tate's general strategy. So, let's take the algebraic extension QP bar. It lives over QP, but I'm going to put something in. Let's not go all the way up to QP bar. Let's instead go to QP and adjoin all roots of unity. That is the cyclic homotopy. So this field over this one is a lot easier to deal with. Its Galois group is the abelian group CB. The rest of the group, I don't know, it's called H. And Tate proves two facts. So one fact has to do with this extension. This field is interesting. It's not p-adically complete, but if you completed it, you would get a perfectoid. And Tate's part 1 is to say that there's actually no interesting cohomology happening between here and here. So if we were to consider the same question, what is the cohomology of the Galois group H acting on C? Well, you actually put something a little bit more fun. Acting on root of integers. You can invert P later to get that action on CP. And Tate shows that for all I greater than 1, this group is almost 0. I killed by any alpha in QP mu P infinity of absolute value less than 1. Origin for any subtotal. In other words, the action of the ring of integers on this by multiplication factors through the multiplication on the residue. Okay, it's for SLU. So in modern terms, we actually know this to be true for any perfectoid field. There's no Galois cohomology over a perfectoid field. And at least integrally, it's almost zero. If you invert p, it's good. So this is one thing that Tate observed. Tate proved it using some very clever ramification theory.
But you mean to write I greater equal than 1?
For all I greater than or equal to 1. Right? In other words, it's acyclic. Galois homology is acyclic over something. And so that really reduces the question to the Galois homology of this object. And now we've just got this nice feeling. So part 2, which is still very difficult, is to show that the map on the homology of 2p cross, let's have that on QP. And then you can map this into the homology of 2p cross acting on. All right, there it is on. UP infinity, and then X. It's really the letter, wasn't it? That says the completion of the signature. Yes.
So about 1, so
Yeah.
it's almost 0. Is it also non-zero?
That's a really good question. I don't know. I don't know anything about the nature of this thing. Really not at all. For all I know, it's infinitely generated, but it's still almost here.
Sorry, so in fact, in fact, I just requested it. So there's no uniform answer, right? I mean, it's only for each type.
Well, there's no uniform,
Because they could be killed by.
but no, it's killed by all alpha. So it's true that,
sorry.
yeah. It's not killed by just one, it's killed by every alpha, no matter how close to one it is. That's the key here. Okay, so then, yeah, this is a nice one. So the thing that we cared about, this is all that's left of the Galois homology. It's actually isomorphic to something much simpler. This is acting trivially though. And this is basically it's a pro P group. It's a abelian of rank 1. You can cross some portion that doesn't matter. And this is kind of the same as 2p. That's why these equals. Part 2 is very, very hard. He shows that Tate shows that actually this has a complement inside of this. There's something incredible called a normalized trace map that exists from here down to here. And you can kind of split off the complement, and Tate carefully shows that the complement exists. Right, so why do they do all this? I just want to suggest to you that these sorts of difficult homology problems can often be separated into 2 tiers. First, pass to something perfectly, and then observe, and something you've passed to is a kind of tractable group. The rest of the way should be trivial. It's perfectly so magical, and we kind of don't have it. So given what Tate did all those decades ago, we can now move on to some statements about higher dimensional adsets. So this was all in secret. The pro-étale homology of the points on QP. That's the term book. Next. The next chapter is pro-étale. So regarding the previous chapter, that dealt with CP as an extension of QP. So think about the nature of this extension. It's not an algebraic extension. Instead, CP is the completion of a colimit of finite étale extension. Okay. So that notion is called pro-étale. It's the completed colimit of finite étale. And this notion extends to more general basics. So this concept of the pro-étale extends the various x's I might want to consider. So it could be an adic space, or it could be a perfectoid space. And in fact, if you're finite A tall over perfectoid, you're still perfectoid, that's a theorem of Schultz's. So you remain in this category. Or there's even more exotic things like V-stacks. That category contains those quotients that I had written down before, like for instance, this one is a V-stack. It's a stack in the category of perfectoid. Under the V topology, the V topology is a lump, a flat. So what you get out of this, once you construct it correctly, and that construction, oh yeah, so the construction for schemes is due to Bott Schulze, and then Schulze developed the concept really far in the context of atoms. So we get a site X really small. And on that side, we've got sheaves. Yes. Oh, I'll just write those as OX. And OX plus. And that's what we have. There's an adic space has a usual structure sheaf. But let's just observe now that that won't do in this case, because this is not an adic space. It's the quotient of an adic space by some terrible group. And there's no like analytic topology that would be appropriate here. You have to pass to some pro-étale cover of this, namely this one, before you start seeing any functions. So the appropriate thing to do in this situation is take that isomorphism of V-stacks and compare the pro-étale cohomology with exact plus coefficients. So I do this, I do this. So as an example, there's the one we just did. So there's an example of what is the pro-étale cohomology of an adic space slot cubing, maybe with O coefficients. So if I had done a different topology like the étale topology, that would be like the Galois cohomology of just the field QP. But that would be acyclic already because of the normal basis theorem or something. But in pro-étale, it works differently. So there's a maximal connected pro-étale cover of spot QP, namely spot CP. And that's Galois, and the group is the Galois group. So this is sort of naturally the same as the Galois cohomology. With action on CDP like this. And this was the subject of Tate's theorem, right? Yeah. So Tate's theorem is an example of a computation in pro-étale. So how would more general sorts of spaces work? Well, this was investigated by Bott, Laura, Schulze, the first paper of theirs, the one that was called Integral P-adic Hodge Theory. So it relies on two steps, just like before. One of them is due to Schulze, and it says that if X I guess I never explained this notation, but you should really ignore it for now. If X is a perfectoid space, that's aphanoid. Then it doesn't have any interesting O colon. More precisely, the ith cohomology of X pro-étale with the coefficients in OX plus is almost zero. For all I at least do. So there's no interesting pro-étale cohomology on an affluent space. And so if it's perfect. So that suggests, just like with Tate, a general strategy for figuring out the pro-étale homology of non-perfectoid spaces. Find a controllable perfectoid space over it, and then do a computation in group homology using a group that's easy to compute with. Maybe it's even an abelian group. Right? So, oh yeah. So as another example, and this example really it's before shows that it really goes back to what if x is not perfectoid? Maybe x is going to be CP and the brackets x. I guess the second coordinate would be OCP and the brackets x. Okay, now I regret not introducing this notation before. Oh, whoops, I have to do plus minus one. Yeah, that's the word. All right, so
Can I ask a question? What happens if we take the homology of not OX plus, but simply OX?
oh yeah, so over a quasi-compact space like this is, that's simply a matter of inverting P on the answer. So if you invert P on something almost zero, so zero, and that's what we care about. Okay, what is this supposed to mean? It's simply the p-adic completion of the polynomial. You can think of it as power series in X and X inverse that converge on the closed unit disk of radius. This is an example of a Hoover ring. The ring, well, this is an example of a Hoover ring also. This is the I read the definition, and the ideal definition is just so okay. This is the one of Tate's. You realize I used X. So I made this a bold. So this is an example of an athenoid adic space. What's its Croatoc homology? So the strategy would be to find some perfectoid cover. And there's an answer that suggests itself. How about x tilde mapping to x? And this is just the one where you extracted all Keith power groups. And imagine what happens inside board group. So you've extracted a Keith root of x and then a P squared root and all the way up. And this notation, well, yeah, it's again the p-adic completion of the corresponding polynomial ring in X and all of its P power roots. So that extension is pro-atal. Let's think about what it's pro-atal because I inverted X. I mean, I inverted X and then I took all these piece roots. That turns out to be atal. So now, what is the Galois group of that? So it's a torsor for the action of some group. Well, you can replace X with any root of unity of P power order. And so I would say that the Galois group it's pro-cyclic. It's like ZP takes us one. So this tells you that the cohomology H star of X pro-atal with coefficients in O plus is isomorphic to almost the group cohomology of ZP1 acting on O plus evaluated on the stuff above O plus of X of golden. And this thing, well, you know what this is, and you kind of know exactly what this does over here, so you can go ahead and compute this. So it's just not hard. And this is how this sort of faulting this insight into how you might proceed in such a concept. So now we can, yeah. I'm going to conceptually fit a lot in one line. We'll close this. So this sort of thing is investigated in detail in the first paper of Bott, Morrow, and Schulze, and that paper concerned smooth formal schemes over OCP. And then it was extended to semi-stable formal schemes by Setsnevicius. in the semi-schema. So they investigated what happens when you take a more general ridged analytic variety, like one coming from an Ethereum Hoover ring like these, and you try to figure out what its pro-atol cohomology. They discovered a link between that and differential forms. But this is what we ended up using. So using those results, our work shows here. All right, so the relevant calculation in pro-atol cohomology works like this. The cohomology of, okay, there were two important spaces. One of them was LTN0. And we want this is with O plus coefficients. And I would say that just as written, this is actually kind of mysterious. But when you invert P, a lot of the mystery goes away. And in this case, I mean, there was a question before about how you get O from O plus. It's straightforward when the space is quasi-compact, but the space is not quasi-compact. What is this space anyway? LTN0, it's an open unit disk over the field W of K invert K. So geometrically, that's all it is. So it's the p-adic analog of the complex open unit disk, and that's certainly not quasi-compact. Okay, great. What's this thing? It turns out to be isomorphic to just the H0. In other words, this is acyclic. And what's the H0? It's the ring AN inverted P. Oh, whoops, there's one more. So putting the diamond here doesn't make a difference because the two objects have the same pro-atol site and the same structure sheath. So the diamond is sort of optional. And I realized I made a mistake here. I was supposed to also isolate an epsilon. So where did the epsilon come from? It came from the fact that this guy doesn't live over CP. It lives over the local field, this one. And that behaves kind of like QP. So there's something coming from arithmetic here. Basically, this epsilon comes from Tate's theorem. It comes from the Galois cohomology of this local field. But then there's also something geometric coming from the computations that happened here. But it turns out that when you descend those computations from CP down to this field, all that other stuff with differential forms goes away. So the result turned out to be kind of convenient. That's part A. The other cohomology result was about Drinfeld's symmetric space. So that's Hn minus 1. How does this work out? And this works out very easily. It's just QP adjoint epsilon. So actually, both of these results are saying something similar. There's no interesting higher cycles in either case coming from geometry. All of the higher cycles just come from arithmetic. And you get QP here. QP actually is O plus. So by the way, well, ZP is O. So the global sections of Drinfeld symmetric space of O plus turn out to just be ZP. Why is that? You can think of Drinfeld symmetric space as dense in something proper. And just think of complex analysis. If I told you if I have a holomorphic function defined on P1, take away a few points, and it's bounded. A bounded holomorphic function extends over the missing locus. So it's just going to be a bounded function on all of P1, so then it just has to be constant. Well, the same logic works here, and O plus of this space just works out to be ZP. So not very interesting at all. So you get this. So we're ready for a discussion of the proof of the main theorem of the day. which has to do with group cohomology, but it takes this detour into pro-étal cohomology. So starting with the isomorphism of stacks from before. So what is it? H, LT, and 0 diamond modulo GN. Isomorphic to HN minus 1 modulo GLN ZP. What we do is apply, we take the O plus cohomology in the pro-étal site, and then we invert P on either side. So on the left side, we get the cohomology of the stack, but that just turns out to be the group cohomology of Gn acting on the cohomology here. So we know what that is already. We have the cohomology of Gn acting on the cohomology of this, but we already know what that is. The cohomology of Kn. An. Then there's this epsilon sticking around. The Gn doesn't act, the Gn acts trivially on that epsilon because it came from arithmetic somehow. It didn't come from the geometry of the situation. So this becomes isomorphic to the cohomology of GLN ZP, always continuous, of GLN ZP acting on what now? The QP. And actually, this is the isomorphism we wanted, except that there's this epsilon hanging around. But that's okay. You can cancel the epsilons by doing it by comparing dimensions on either side. If you want the details of this, just remember that this thing admits a map from, well, okay. If you want, I can give you more details of this, but I'm excited to share some more things. I'm just gonna wave my hand a bit to say compare dimensions. So you get an isomorphism without those kind of annoying epsilons on either side. Okay, but that's the strategy for how this isomorphism was proved. And it worked really well in this case. And what was this case? It was relevant to the transchromatic splitting conjecture in heights n and 0. So in the last part of the talk, I want to discuss some possibilities for extending this to other heights. So this is all work in progress with all of the collaborators that I mentioned yesterday.
Quick question. So you say that the epsilon only appears in arithmetic picture,
Yeah.
is that? So I wonder whether you can rephrase this as something like push forward from TLT and this thing to like phi QP, then you don't have any higher cohomology. I mean, push forward. I mean, the theory. I mean, you can say radical. No, the theory. The upper, yeah.
Yeah.
I'm not sure whether I understand from both basic maps to span QP or something.
Yeah.
And then you can describe the higher push forward.
Yeah.
And is that true that this higher push there's no, I mean, how to say, there's no cohomology for that higher push forward. I think that this is a consequence of.
Are you suggesting an improvement on this or a different way of
No,
understanding
that's
it?
Maybe in interest of time.
Yeah, let's move on.
Okay.
Yeah. All right, last section. Beyond all this. Okay. So here's the theorem of godless. I mean, it seems it's progressed beyond this case of N0 towards the case of NT, where T is arbitrary. We need something about a different stack. So the stack in question is LT and T, and then diamond modulo G and same kind of thing. So I want to tell you what this that actually is. So, remember that AN was, the ring of fit vectors, and then we have to join all these variables. And what I want to do is take this ring, mod out by all the variables up to t, t minus one, and invert the t variable, and then take the slot. And this works out to be something rather nice when t is equal to n minus one, you just get a Laurent series. So we get this kind of new stack involving LT and T, but when T is positive, we can mod it out by P, and now we're entirely in characteristic P. So this is completely in characteristic P. All right, there's something on the other side, and we already know what it is. So I'm gonna write it this way. It's some kind of mystery object, omega n T. We'll play it out in a second. Modulo, and here's where I want you to pay attention. GLN minus T of ZP cross the Morava stabilizer group GK. So the appearance of this group was enormously satisfying to me because this is exactly the group that Andrew Sanger proposed should appear in this situation. So it's now appearing in chaotic geometry very naturally. Okay. So the promise of this is that we might hope to prove, first of all, some kind of acyclicity result for the mystery object that I have in 25 seconds. Meaning no higher cohomology, and the zeroth cohomology is this constant, so just piece of that p bar. On the way to proving a conjectural result about the cohomology of Gn acting on that ring and modulo So, this or some closely related version of this was what I call the algebraic transchromatic splitting conjecture. This was the one where if you could prove it in the case of t equals n minus one, you would get the spectral version of the strong chromatic splitting conjecture. But in the cases in between, I don't know how you get anything spectral out of the statement, but it is interesting. So, another trend. I'll say one more line about this omega nt is. It is kind of crazy. So omega nt is an example of a diamond. This is Schultz's category of diamonds. They're like algebraic spaces. They appear when you take a perfectoid space and you quotient by some pro-étal equivalence. So it's a mild extension of the notion of perfectoids. And I'll tell you just something about the nature of this thing. It lives in a certain vector space called a Banach-Holmes space. The slope of that space is negative 1 over t, and I've got to take n minus 3 copies of it. it seems I'm gonna have to leave unsaid what this thing is. But there's some great literature on the subject. Wouldn't like Valdez. It is a QP vector space. It's a QP vector space object in the category. And just one copy of it already has an action of GP, and we're on the state one. But if I take this many copies of it, then there's an action of not just GT acting diagonally on all the copies, but also the product of GT by GL n minus T QP. Simply by dint of the fact that BC is a QP vector space. So that when you take this many copies of it, then you can act upon it by matrixing. So that explains the action and the appearance of this group on the space. For much more on this, okay, I can, well, okay. Maybe I can refer you to my IHES 22 notes. Now, what a BC space is, I can also tell you that this is the complement of all QP linear hyperplanes. So it sort of is an echo of Drinfeld symmetric space, and that it lives inside of some vector space, and it's the complement of all the QP linear hyperplanes inside of it. So it's a fantastic story that's still developing, and so I hope you've taken to heart the power of p-adic geometry as a tool for studying homotopy here. Thanks a lot.